fire its engines, and bid farewell to Asteroid Bennu.
Hello everyone! Today is a big day at NASA. After 2.5 years of space operations near Asteroid Bennu, NASA's first asteroid return mission, OSIRIS-REx, is ready to bid farewell to this fascinating rocky object. I'm your host, Joy Ung, and I'm joining you from NASA's Goddard Space Flight Center in Greenbelt, Maryland. We're about 20 minutes away from witnessing the exact moment OSIRIS-REx begins its journey back to Earth and starts a new phase in its mission. This journey will take more than 2 years and will be the largest sample return since the Apollo astronauts brought back rocks from the moon in the 70s. So this is really exciting. In today's show, we have a great lineup. We're going to take you inside Lockheed Martin's mission support area in Littleton, Colorado, as we depart Asteroid Bennu. We're going to show you the last images of Bennu taken by OSIRIS-REx and explain why the mission chose to make one final encounter with the asteroid. And helping us tell those stories will be the current OSIRIS-REx team. This is a really special moment for the team because they've been working together for many years and they're about to finish their stint on the mission as the spacecraft heads into its new phase. So if you have questions for any of the team, head to NASA's Solar System Instagram to pop your questions in our stories. You can also track the mission by following NASA Solar System on Twitter, Facebook, and Instagram, or by following the hashtag #ToBennuAndBack. So there's a team watching OSIRIS-REx's every move as it orbits Asteroid Bennu. They're based at Lockheed Martin Space in Littleton, Colorado. This is where OSIRIS-REx was built and where mission controllers receive its data and can tell how it's doing. So let's check in with them now to get an update on today's big event. Hi, Lauren. How's it going?
We're doing great here, Joy. I'm Lauren Duna, and we're here in the Lockheed Martin Mission Support Area outside of Denver, Colorado, where a team of engineers is flying OSIRIS-REx right beside us. With me today is OSIRIS-REx's propulsion lead, Carrie Parrish. Carrie, can you tell myself and our viewers what's going to be happening here today?
Sure. So today we're going to be using our largest engines in order to change OSIRIS-REx's velocity relative to Bennu and get it started on its journey back to Earth. Now, today's activity is similar to maneuvers that we've executed at Bennu over the last 2.5 years. The main difference, though, is that we're going to fire our thrusters for a much longer duration in order to really kick up the momentum of the spacecraft back towards Earth.
So this will be OSIRIS-REx's longest engine burn since it's been at the asteroid Bennu. About how long will the departure process take today?
Well, the maneuver itself lasts for about 7 minutes, but our team has been working for the last several weeks to optimize the magnitude of the burn and the direction the spacecraft is facing when the thrusters fire. Our main engine maneuver sequence, which is responsible for executing all the commands on board, was started about an hour ago.
That is so exciting. Well, I know I can't wait for what happens here in just a little while. Thank you so much for joining us today, Carrie, and good luck to you and the team.
Thank you, Lauren.
So after today's engine burn, OSIRIS-REx doesn't exactly have a straight path back to Earth. The spacecraft will actually have to surf using some pretty cool orbital mechanics to propel itself home. Joining us now to talk about that is Mike Moreau, OSIRIS-REx's Deputy Project Manager at NASA's Goddard Space Flight Center. Mike, how are you doing today?
I'm great, Lauren. I'm really excited to be here with our Lockheed Martin and Kinetics team members to get the spacecraft headed towards home.
Well, we're very excited to have you and very excited for today. So fast forwarding a little bit, after OSIRIS-REx heads back to Earth, how will the sample return capsule actually get back to Earth?
Well, that's a good question. So Bennu is in an orbit that's very much like the Earth's orbit about the sun. But right now, Bennu is actually on the opposite side of the solar system from us. So following the maneuver today, the spacecraft will be moving rapidly away from Bennu, but it will still take almost 2 years or 2 full orbits about the sun for OSIRIS-REx to catch up with the Earth. So after that journey, the sample return capsule will be jettisoned from the spacecraft in September of 2023, just 4 hours before atmospheric entry. And the satellite, OSIRIS-REx, will perform its own maneuver to divert and fly safely past the Earth.
Well, I know I can't wait to see what the spacecraft brings back to us in its sample return capsule. So reflecting back a little bit on what the mission has done to date. So OSIRIS-REx launched in September of 2016 and arrived at Bennu in December of 2018. But after it arrived, it didn't just stay in orbit like most planetary missions. Why was that?
Well, the short answer, Lauren, is that Bennu's gravity is much weaker than that of a planet like Mars or Jupiter. So flying in the vicinity of Bennu is more like a dance. It takes only tiny nudges to send OSIRIS-REx changing direction to execute the next flyby or to capture into orbit or whatever the next dance move is. So OSIRIS-REx is still attracted by Bennu's gravity, but that force is so small that the spacecraft is also pushed around by the sun's radiation pressure on the solar arrays and from tiny accelerations from heating and cooling from surfaces of the spacecraft. So that's what makes Bennu so challenging, is the precise modeling that has to happen in order to do this dance around Bennu.
Absolutely. That sounds super complex. And it sounds like that it's actually not that easy to fly in low gravity.
No, it's required a monumental amount of effort by our operations and navigation team members, some of which are sitting in the room here today.
Absolutely. So I know we actually have a video out there of the complex web that OSIRIS-REx made around Bennu. Can you talk us through that?
Yeah, that's right. It's called the Web Around Bennu, and it maps out every trajectory arc in orbit performed by OSIRIS-REx since 2018. When OSIRIS-REx first arrived, it made a series of flybys over Bennu from about 5 miles away. Then it captured into an orbit at the end of 2018, just a mile above the surface. And this pattern of leaving orbit, conducting flybys, and returning was repeated through subsequent mission phases, each time getting closer to Bennu to observe in greater and greater detail. So in 2020, we began conducting rehearsals, and we had the same pattern of getting back into orbit after each activity. Then after the successful tag in 2020, in October, we drifted almost 2,000 kilometers away from Bennu. But at the very end of the animation, you can see that we came back for one last flyby on April 7th to see how we disturbed the tag site from the sample collection event.
Wow. So I know that really looks like a tangled web indeed. And so did the team learn anything from doing all these very precise maneuvers around the asteroid that we could apply to future missions?
Yes, absolutely. Every kink in this trajectory means the spacecraft performed an extremely precise maneuver, changing its velocity by 2 to 20 centimeters per second. So each of those resulted in a huge effort by the team here in the room. So on the next small body mission, I believe we'll be able to use some of the autonomy and onboard smarts that made our tag event so successful to ease the burden on the team members over the 2 years of operations that we did.
That is so exciting. And again, it's always great to have a mission like this, but even more important that we learn things to take forward. Mike, thank you so much for joining us today. We're so glad you're here, and I know we'll see you back a little bit later in the show.
Thanks, Lauren.
So as we wait for OSIRIS-REx to begin its journey back to Earth, let's take a brief look at its most challenging event at Bennu, the moment it slowly descended to the surface and reached out its arm to touch an asteroid. Wow, that is such an exciting moment. I just love seeing that footage. You can see just how much loose material is flying around in those images taken by the spacecraft. TAG was a huge success for the mission. OSIRIS-REx collected a substantial amount of rock and dust, but that success created another hiccup. A little while ago, we asked Ryan Olds, the guidance, navigation, and control team lead, what happened after TAG? Let's hear what he had to say.
The tag moment itself, we had no way to really know for sure how much was in the sample head. Seeing those first pictures, me personally, I went from absolute excitement to just being stunned. Initially, we saw we had a ton of material in the sample head, But the more and more images we started to see, the more we started to pause and say, wait a minute, we're starting to lose some of this sample. So we had to look through a lot of these images to determine what was going on, how much sample we had, if there was any risk to stowage. Because there are some possibilities of the material getting in the way and blocking the sampling mechanism from stowing properly. We started to realize, hey, we might have to make some changes here to be successful. So in order to know that the sample was stored safely, we relied a lot on images from our StowCam camera, which took pictures of the capsule and the sample head getting stowed into it. It was a very challenging process. We had not practiced that procedure since before launch, when the spacecraft was in the high bay. To go through that process, taking all the images as we carefully moved the sample head into the capsule was extremely exciting, extremely challenging. It all went off without a hitch.
That was a precarious moment for the mission. After all of the hard work that went into tagging Bennu, OSIRIS-REx was almost a victim of its own success. But to tell us more about how the mission adapted to the rough surface of Bennu, we have the OSIRIS-REx principal investigator from the University of Arizona, Dante Loretta. Hi, Dante, how are you?
I'm very excited, Joy. This is a great day for the mission.
So we just saw OSIRIS-REx create a lot of turbulence on Bennu during its sample grab. What did the flying debris reveal about the asteroid's rough surface?
One of the biggest uncertainties when we were designing the mission was what was going to happen when the spacecraft made contact with Bennu. And we had predictions ranging from a fraction of an inch to 3 feet deep that arm would sink. We were much more on that latter perspective. The spacecraft was penetrated deeply into the asteroid surface, and the surface responded almost like a fluid. I like to compare it to one of those ball pits at a kid's playground. So we learned that the surfaces of these rubble pile asteroids are very loosely consolidated.
Well, that was a really dramatic maneuver. So why do we need an asteroid sample?
Asteroids are the geologic remnants from the dawn of the solar system. We want to understand, how did Earth become a habitable planet? How were the seeds of life, those prebiotic organic materials, delivered to Earth that trigger the origin of life and evolution as we know it? So we have to go back to the rocks that date from that time of solar system history, and that is where you find the asteroids.
Well, I'm so excited that the sample is finally coming back. So after tag on April 7th, 2021, OSIRIS-REx made its final flyover of Bennu. Why did you send OSIRIS-REx back to survey Bennu after collecting the sample?
Well, we've all seen that amazing footage of the day that OSIRIS-REx contacted Bennu and sent that debris flying everywhere. And everybody wanted to know, what did the surface look like? The good news was, after we checked out the spacecraft, everything looked really healthy with no sign of any degradation whatsoever from the tag event. The flight dynamics team also did their calculations and said today, May 10th, was the best time to leave the asteroid to conserve fuel on the spacecraft. So we had a healthy spacecraft and we had time. I told the team we have to go back and get those final images.
And so what did you learn?
Well, we definitely left our mark on the asteroid. We're seeing a pretty large crater. Extensive amounts of material was mobilized. And so it really helps us understand the nature of the asteroid surface and gives us some insight into what we might be bringing home.
Great, thank you. And so thank you so much for joining us, Dante. So we're about to head to the mission support area. So let's go back to the Lockheed Martin to watch OSIRIS-REx depart Bennu.
Thanks, Joy. We are just about 2 minutes away here from the initiation of the departure burn. And with me, I've got Jody Zareski, who is OSIRIS-REx's systems lead here at Lockheed Martin. Jody, what are we moments away from happening right now?
So right now, the team is awaiting ground confirmation that the burn has started via the Doppler plot you see behind us.
So I'm not sure if you all could hear that, but we just heard the 1 minute countdown has started to the initiation of OSIRIS-REx's engine burn. While we're waiting for that to hit, Jody, one question for you. So OSIRIS-REx is 291 million miles away. What is the communications delay like during that time?
So today's one-way light time is about 15 minutes and 56 seconds.
Gotcha. So did the team upload the commands to the spacecraft prior to today?
We did. All the products necessary to execute today's maneuver were sent this past Friday.
That is super exciting. Well, we'll go quiet here and listen to the room as we're just a few moments away. Jody, what have we just heard?
We just heard that settling burn has started.
That is super exciting. So while we're kind of waiting as the team waits and watches the spacecraft here, can you tell me a little bit about what your role is on this mission?
All stations, navigation has received confirmation of settling burn start.
So that was the confirmation of OSIRIS-REx's engine burn start. There's a lot of excitement here in the room today. We're super excited for this moment to happen. Jody, how are you feeling right now?
Oh, I am so excited. I really wish Motley Crue was here so we could rock out to Home Sweet Home because we are bringing that sample back.
Absolutely.
Navigation has received confirmation of main engine burn start.
Yes.
All good news here at Lockheed Martin. Joy, I'll send it back to you.
Thanks, Lauren. So while we're waiting for the completion of the engine burn, let's take a quick look ahead at what will happen when OSIRIS-REx reaches Earth.
After departing from Bennu, OSIRIS-REx will return to Earth in late 2023. 4 hours prior to arrival, the spacecraft will release the sample return capsule, then deflect away from Earth to its final orbit as its piece of Bennu comes home. The capsule will enter the atmosphere over the night side of Earth, streaking towards the central California coastline at over 12 kilometers per second. West of the Great Salt Lake, at an altitude of approximately 33 kilometers, the capsule will initiate its parachute sequence, stabilizing and slowing its descent. Upon landing in the Utah desert, the sample will be recovered, carefully removed from the capsule, and taken to the OSIRIS-REx Curation Facility at NASA's Johnson Space Center in Houston, Texas. This pristine material from the early solar system will be studied for decades to come, providing clues to the formation of the planets, to the evolution of Earth, and to the ingredients that were present at the origins of life.
Welcome back. My name is Joy Ng, and I'm talking to you from NASA's Goddard Space Flight Center in Greenbelt, Maryland. If you're just joining us, OSIRIS-REx has fired its thrusters and begun the departure maneuver from Asteroid Bennu. We're going to send you back now to Lockheed Martin to watch the rest of the OSIRIS-REx departure from Bennu.
Thanks, Joy. We're back here at Lockheed Martin, and joining me again is Mike Moreau, the NASA Deputy Project Manager for OSIRIS-REx. Now, we're awaiting the announcement for 50% completion of the burn for departure. Mike, how are you feeling right now?
I'm feeling really great, Lauren. We've got good news. We're seeing on our displays that the burn is executing. We're seeing these Doppler points propagate on the plot, which tells us we're making progress towards the burn, and I think we're a couple minutes away from that midpoint.
Well, that is just fantastic to hear. So while we're waiting for that midpoint, let me ask you, do you think this is a mission that we could have done 30 years ago?
No way. We're really pushing the envelope with our 21st century navigation and operations capabilities to fly a mission like OSIRIS-REx. Just a couple of examples, the navigation, the maps for landmark navigation that we used on the mission required exchanging gigabytes of data and these large files containing topographic maps of Bennu, which would have been a challenge with yesterday's computer systems.
Also,
another example.
Completed 50% of the ADM burn.
Okay, that's the call you were looking for. We're halfway done the burn, so we're about halfway through the 7-minute main engine burn. So that's very good news. Just to finish what I was saying, so the other example I was going to make is the NFT system. For those of you that followed the sample collection event, we had an onboard system called NFT that was used to navigate the spacecraft to the surface. The Lockheed Martin team that developed NFT had to do a lot of work to get that software, which was running processes that we normally do on the ground in our computers here, to get that to fit in the capability of the onboard processor on the spacecraft. So that's just a couple of examples, but there are many things like that where we really had to push the envelope of our capabilities to fly this mission and fly so close to Bennu and ultimately touch the surface.
Absolutely, especially something like that natural feature tracking where you're doing such proximity operations to an object that you really need that real-time data and that real-time ability for the spacecraft to maneuver itself. Yeah. So I want to reflect back really briefly. New Year's Eve 2018. I know there's a picture out there of you and the whole team here all dressed up in formal wear to go to work. Why did you guys do that?
Okay, well, we mentioned earlier, that's a great picture. It's a great memory for the team. I mentioned earlier that we had our first insertion into orbit December 31st of 2018, and that was an event that was a big milestone on the project. It was the first time we'd ever been that close to Bennu, and we were worried that we might be surprised by something new. So we figured if we had to do this big event on New Year's Eve, we might as well get dressed up and celebrate in the process. And it was a lot of fun. This picture actually was taken about an hour after we confirmed we were successfully in orbit. We went outside. It was about 10 degrees and snowing, but we toasted our success with sparkling apple cider while it just happened to be midnight GMT about that time when we went and did that. So it's a great memory, and it really just gives you an example. The team has worked so hard over the past 2 years to accomplish this exploration of Bennu, really sacrificing a lot, but they knew how to have fun too, and it was a really great team. So
that is such a cool memory, and I'm sure not a lot of people can say that. That is super exciting. Mike, about how far out are we now from the completion of the departure burn?
So we're getting close now, I would say, from the plot. We're probably a minute or a minute and a half from the final call out. So let's listen for that to happen.
Absolutely. So we're going to give a listen into the room now as we're waiting for OSIRIS-REx's engine burn to officially complete.
All stations, the ADM burn has completed. We have a nominal ADM burn, and we're bringing the samples home.
So exciting. Mike, how are you feeling right now after all the time that you've spent on this mission?
Well, I'm very, very excited. I'm thankful that this event is over. I mean, we've done maneuvers like this many, many times, so we had confidence that would go well. But now we know the spacecraft's coming home, or the culmination of all of our hard work. So it's really exciting to be here. It's also a little sad to be leaving Bennu, but that's what we need to do to bring the sample home.
Absolutely. Well, I am super lucky to be here witnessing this moment. I know we've also got program manager Sandy Friend here as well. Sandy, after someone such as yourself, I know you and Mike have been on the mission for such a long time. What does this feel like to you right now?
Yes, this is really kind of bittersweet. We've spent over 2 years at Asteroid Bennu, really getting to know it. But the prime goal of this mission is to bring that sample home. So we set out, we did what we were supposed to do at Bennu. We've got those samples in hand, and it's time to bring them back. So I'm really excited for this next phase and to see what the scientists learn once they have these samples in hand here back on Earth.
Definitely understand that bittersweet feeling. I can't even imagine, how you must feel and how excited you must be. But thank you so much for being here with us today, Sandy. And congratulations again to you and Mike and the entire OSIRIS-REx mission team. Joy, we'll send it back to you for some questions from our other team members.
What amazing achievement. I'm so excited. So joining us now is Dr. Laurie Glaze, who is the director of NASA's Planetary Science Division from NASA headquarters. Hi, Laurie, how are you doing?
I'm doing just fantastic. Thank you. I want to say congratulations to the whole team. That was incredible. Nicely done. Nicely done, as always.
So what has NASA learned from OSIRIS-REx's success that will be applied in the future?
It's a really good question. And you heard Mike speak just a little earlier about the importance of, for example, the autonomous operations that were demonstrated by the OSIRIS-REx spacecraft and the operations team that'll help inform future small bodies missions. But there are a variety of other things we've learned as well. For example, most of our planetary missions take their observations from a distance using remote sensing instruments to help us understand the composition of those planetary surfaces. But it's really rare that we're actually able to collect a sample and bring it back to Earth that we can then use as ground truth to help us calibrate those remote sensing observations. So we have a really unique opportunity here to use the samples that we've collected to help us interpret those remote sensing observations. And then on future missions, when we're taking remote sensing observations, we'll be able to better interpret those and better make conclusions about what the surfaces of other bodies look like, or what they are.
So what's next for NASA's small body missions after OSIRIS-REx?
Another great question. So small bodies are incredibly fascinating, and there are, of course, many, many small bodies across our entire solar system. And we find them in different locations, and the asteroids we find in each of those locations can tell us little bits or different parts of that story about how our solar system formed and how it evolved over time. And so the next mission that we have ready to go that's going to launch in October of this year is called Lucy. And the Lucy mission is going to go to study a family of special asteroids that are trapped in Jupiter's orbit. It's actually going to visit 7 different asteroids that are called Trojan asteroids in that Jupiter orbit to help us understand the formation of those giant planets and how their history impacted the formation of those different asteroids and Trojan asteroids found in that orbit. And then the next mission after Lucy that we're going to launch is called the Double Asteroid Redirection Test, or DART. And that mission is going to launch in November. So just a month after the Lucy launch, we'll be launching DART. And DART is our first mission in our planetary defense line. And so it has a really important purpose to demonstrate a new capability, test a technique called the kinetic impactor technique, where we're going to show just how well we can change the orbit of a very, very small asteroid by impacting the spacecraft into the small moon of the asteroid Didymos, and the small moon is called Dimorphos. And we're going to impact that spacecraft in there and see just how well or how much we can change its orbit around the larger asteroid. And then we have another mission coming up in 2022 called Psyche that's going to launch in the summer of 22. That mission is going to visit a special asteroid called 16 Psyche that appears to be a very metallic asteroid, a very unusual asteroid that could potentially be the core of an early planetoid. So we're really excited about that mission as well. We're all set to learn lots of great information about the small bodies that inhabit our solar system.
We have a busy and exciting few years ahead of us. Thank you so much, Lori.
It's my pleasure. Thank you.
Now I'd like to bring back OSIRIS-REx principal investigator. Dante, how are you feeling?
I'm actually a little more emotional than I expected to be right now. We knew this maneuver was coming up, but to see that Doppler plot and to know that those engines fired, it's just an amazing sense of pride and accomplishment. I couldn't be more excited for what this team has accomplished. At moments like these, I always think about the spacecraft and just imagine it 200 million miles or more away from us doing everything that we're asking it to do. And today we're asking it to fire those engines. It's now moving away over 600 miles an hour from Bennu on this way home.
I'm so excited for you. So OSIRIS-REx has collected a lot of data over the past 2.5 years. As the principal investigator, what are you most excited about?
Well, OSIRIS-REx is all about sample return, and we picked Bennu for a very special reason. We believed from our astronomical telescopic data that it was rich in carbon, primarily in the form of organic molecules, and that it contained abundant water locked up inside minerals called clays. So for me, the most exciting results were when we got the spectrometer data down. And first we saw that clear signature of water all over the surface of Bennu. It's a very wet, hydrated rock. And then a little later on in the mission, we got the signal that there was abundant carbon, and it was everywhere on the surface. We picked a great sample site, Nightingale, which we think is going to give us wide representation of the different rock types on the asteroid. So everything I hope that this mission would deliver in terms of the sample, Bennu has given us. So we've done our job. We got the sample. Now we fired our thrusters and we're on our way home. It's time to look forward to what I call the ground game.
Well, huge congratulations again. And most of the people on this team have been together for a long time and have performed flawlessly throughout the mission. So what do you think has made this team so successful?
Well, building this team culture was one of the biggest jobs of the leadership group. And we knew right away, you're bringing together people from an academic institution, from an industry partner, from a government agency, and there's different backgrounds, different cultures, and different motivations. But we very quickly came together. We were not University of Arizona, Lockheed Martin, and NASA. We were OSIRIS-REx. We had a mission. That mission was to build an amazing spacecraft, literally do some world record-setting astrodynamic maneuvers around the asteroid and collect that sample. So that common sense of purpose and that unity is what made this team work so well together.
Thank you, Dante, and congratulations to you and the entire OSIRIS-REx team.
Thank you.
So, welcome back. My name is Joy Ng, and I'm talking to you from NASA's Goddard Space Flight Center in Greenbelt, Maryland. If you just joined us, OSIRIS-REx has officially left asteroid Bennu, and it's on its way back to Earth. So the OSIRIS-REx mission is not over, though. It enters a new exciting phase, delivering the bounty of asteroid sample back to Earth. So we're going to be talking to two people who cannot wait to get their hands on that sample. We have Nicole Lunning from NASA's Johnson Space Center in Texas, and Jason Dworkin from NASA's Goddard Space Flight Center in Maryland. Hi, Nicole and Jason. Thank you so much for joining us. So this is a really exciting time for you both because your work is just beginning.
Absolutely. It's a thrilling time. I've been working OSIRIS-REx to get a sample back from an asteroid since my daughter was in diapers, and now she's graduating from high school. It's I can't wait to get that sample back and say our goodbyes to Bennu.
And I'm newer to the mission than Jason, but I'm looking forward to years of being part of the team that curates and takes care of this sample once it returns to Earth.
So Nicole, can you walk us through what happens after the samples are recovered in the Utah desert? How does the sample get secured and sent to the lab at NASA's Johnson Space Center?
So after the sample return capsule is recovered, it will actually be taken to a portable clean lab we'll set up in Utah for a sort of preliminary disassembly, where the part of the sample return capsule that contains the Bennu material will actually be packaged then into a travel box that will keep it in a nitrogen atmosphere to protect it from contamination from Earth's atmosphere. That will be flown on a plane to our lab at Johnson Space Center that we're currently building, and there have been careful documentation processes of building it, as well as choosing materials to limit very much what the asteroid material will be exposed to really protect it.
That is quite the journey. So in that same vein, Jason, can you tell us a little bit about how you and the team will keep that sample in pristine condition?
Right. So as Nicole was saying, we have a limited number of materials that the sample can be exposed to. This was actually planned out well before we ever started building a spacecraft. In the very, very early days, we came up with strategies to keep the sample clean and to document both in paper, but also in chemical documentation of what the sample has been exposed to, so that when it comes back, we can compare the witnesses, the chemical witnesses of the sample with what we actually get back and understand what the sample tells us about the solar system.
And Jason, you've had such a long career analyzing samples. What excites you most about receiving this sample?
So I'm an organic analytical chemist. So I'm interested in, among our over 50 different hypotheses testing, looking at things involved in the organic compounds that lead to life, like the left and right-hand amino acids, and look at those sorts of things in the sample. But the part that excites me the most is that 75% of the sample we bring back is archived for future generations. So scientists, perhaps not even born yet, will use techniques we can't imagine to ask questions we don't know how to phrase yet. And so this is a decades-long legacy that OSIRIS-REx brings to science to study.
Well, I'm so thrilled for you both. Thank you so much for joining us, and huge congratulations again. So there we have it. OSIRIS-REx has officially left Bennu and is cruising home. You can keep up to date with this amazing mission by following NASA Solar System on Twitter, Facebook, and Instagram, or by following the hashtag #ToBennu&Back. We're now about to close the show with a look back at the best moments of the OSIRIS-REx mission at Bennu. Thank you so much for joining us.
On October 20th, 2020, NASA's OSIRIS-REx spacecraft collected a sample from Asteroid Bennu.
Navigation.
Go for tag.
Program manager.
Program manager is go for tag.
All stations, this is OREX Systems on OREX Chord. I copy all subsystems are go for tag.
Position uncertainty is 0.5 meters. Predicted tag lateral offset is 1.7 meters. Hazard probability is 0%.
OSIRIS-REx's sampling mechanism penetrated Bennu's regolith and fired its nitrogen gas bottle to stir up sample material for collection in the TAG-SAM head. At 6:08 p.m. Eastern, the team on Earth received confirmation of a successful touchdown.
OREX has descended below the 5-meter mark. The hazard map is go for tag.
And we have
After spending approximately 6 seconds at the surface, OSIRIS-REx fired its thrusters and backed away from sample site Nightingale. Images taken a few days later by the SAMCAM camera showed rocks and dust escaping the sampler head. The team believed it collected a sufficient sample and decided to seal the TAG-SAM to preserve the remaining material. The spacecraft made one more flyover of Bennu and saw just how big a mark it left on the asteroid's surface. The TAG event sent boulders flying across Nightingale's surface. OSIRIS-REx completed its last flyover of Bennu at around 6 a.m. Eastern on April 7, 2021, and slowly began drifting away from the asteroid. On May 10, 2021, OSIRIS-REx fired its thrusters and began its 2-year cruise back home to Earth. As OSIRIS-REx approaches Earth, it will jettison the sample return capsule that contains pieces from Asteroid Bennu. The SRC will then travel through Earth's atmosphere and land under parachutes at the Utah Test and Training Range on September 24, 2023. Once recovered, the capsule will be transported to the curation facility at NASA's Johnson Space Center, where the sample will be removed for distribution to laboratories worldwide, enabling scientists to study the formation of our solar system and Earth as a habitable planet.
In December 2018, after traveling for 2 years, 101 days, and over 1.2 billion miles, NASA's OSIRIS-REx spacecraft arrived at its target, near-Earth asteroid Bennu. OSIRIS-REx is the first mission to explore this primitive remnant from the origins of the solar system, designed to study the asteroid and return a sample to Earth. Bennu is a dark, diminutive world, roughly the height of a skyscraper, and now the smallest body to be orbited by a spacecraft. Prior to arrival, it was known to have low thermal inertia, a characteristic of fine-grained materials like sand. An infrared spectrometer on OSIRIS-REx confirmed this property, leading scientists to expect a predominantly smooth surface. But the first close-up views of Bennu delivered a major surprise. In exquisite detail, the mission's cameras revealed an unrelenting rockscape dominated by boulders. By combining these images from OSIRIS-REx with its laser altimetry data, we can take a tour of Bennu's remarkable terrain. The first stop is Simurgh-Saxum. This prominent boulder defines the asteroid's prime meridian and serves as the basis of its coordinate system. In Persian mythology, the Simurgh is a large and benevolent bird and the possessor of all knowledge. Saxum is Latin for stone. To the northeast lies the largest boulder on Bennu. Measuring over 300 feet in length, Rock Saxum is a colossus longer than a football field. It is also rich in a type of iron oxide called magnetite, which was used by mariners as an early form of magnetic compass. In Arab folklore, the rock is an enormous bird of prey that can clasp elephants in its talons, as well as stranded sailors like the hero Sinbad. Continuing northeast over the equatorial ridge, we arrive at Gargoyle Saxum. This striking boulder is among the darkest on Bennu, though it clutches a much brighter rock that is about the size of a person. In medieval legend, gargoyles are dragon-like, winged monsters that can breathe fire and that guard cathedrals from evil spirits. Our next destination takes us far to the east. At the northern end of a small crater lies Ocypity-Saxum, a comparatively bright boulder measuring about 33 feet in diameter. Ocypity-Saxum is located near one of 3 sites where Bennu ejected small particles into space in early 2019, displaying its dynamic and evolving nature. In Greek mythology, Ocypity is one of the 3 harpies, the half-maiden, half-bird personifications of storm winds, who would carry evildoers away from the earth. In the creation stories of ancient Egypt, the universe began as a formless, endless expanse of water. From this primordial sea arose the primordial mound, Benben. It was upon this rock that the god Atum settled in the form of the Bennu bird and sent forth the call that shaped creation. The story of Benben harkens to the mounds of fertile silt that once emerged from the receding floodwaters of the Nile, and it provides a fitting namesake for the tallest boulder on Bennu. Protruding by over 70 feet, Benben Saxum is so tall that it was first detected from Earth. Now, we can appreciate this monumental feature in detail using data from OSIRIS-REx. The final stop on our tour is a cluster of exceptionally bright boulders scattered across the southern hemisphere. They bear the spectral fingerprint of pyroxene, a mineral found in igneous rock that is unlikely to have formed on Bennu. These boulders most likely originated on the large asteroid Vesta and were delivered to Bennu's parent body through meteoroid impacts. Although it is small in size, Asteroid Bennu has proved to be a fascinating world, abundant in geographic features that have defied our expectations. Thanks to OSIRIS-REx, we can now explore Bennu to uncover its composition, its evolution, and its ancient memories from the origins of the solar system.
As we started to approach Bennu from a distance and it started to fill up the camera field of view, it looked exactly like we thought it would, with a few boulders sticking out. But as we got closer, we expected to see a very sandy surface with maybe some few boulders here and there. And what we saw is very little sand. And we saw these mountains, we saw boulders, we saw rocks, and we saw very few areas that had this sandy surface that we were expecting and what we had designed to.
We have never done this before. We're actually going to collect a sample and bring it back down to Earth for further examination by scientists.
In order to achieve that objective, the OSIRIS-REx spacecraft has been navigating around Bennu for about the last 2 years, studying it in great detail. and also overcoming a number of challenges that Bennu has presented. We were looking for locations on Bennu that were 50 meters in diameter, relatively flat, and covered with fine-grained material. And by fine-grained material, I mean stuff that's the size of a dime or smaller. We realized that there were no sites on Bennu that even came close to meeting this criteria. Everywhere we looked was too small and covered with boulders. So we actually had to fly a number of additional closed passes over the asteroid and rethink our entire plan for grabbing the sample. After the additional observations of Bennu, we had to down-select to 4 sites, and then go back and survey those sites even further to select the final primary sample site.
My first impression of Nightingale is that's the last place I wanted to go. But as we started looking at other sites, we saw that 1, this is probably one of the most sampleable sites, and 2, we were overperforming in our navigation capability and our ability to contact. Natural feature tracking works a lot like the human mind in that we pick up landmarks along the way. As we descend, we look at features on the ground. We program the computer to recognize certain features. It takes a picture, says this feature is not where I expected it to be, it's a little bit off to the side, updates its position based on where it's pointed and where that feature shows up in the camera position.
The tag event is our touch and go event, which is where we'll actually be retrieving the sample from Asteroid Bennu. We start with a series of maneuvers, one of them being the checkpoint burn, which is where we'll actually check our position and velocity in relation to the sample site.
And then the match point burn, about 10 minutes later, will zero out our horizontal velocity relative to the surface. And then about 10 minutes after that, we make contact with the tag SAM, fire the gas bottle, and then back away.
And we hope to get at least 60 grams of sample, and then we'll be able to store that and bring it back down to Earth.
But there are several things that could go wrong, and we also have to be prepared that we won't be successful on our first try at Nightingale.
We don't only get one shot at tag, we actually have 3 nitrogen bottles on board the spacecraft, so we can potentially do 3 tag attempts if needed. We go through several what-if scenarios, and this is how we actually prepare for a lot of our contingencies.
So we've had to look all around the surface and identify the rocks and boulders that if the spacecraft were to tip over up to 25 degrees, it could come into contact and be damaged.
We had to develop a hazard map, which we program into the computer and says, if you're getting too close to those hazards, we'll do a wave off, we'll back away from the asteroid, and we'll come back and do this another day.
Everything might work perfectly. We come down, we touch the surface just where we want to, we fire the gas bottle, but the area we contact is covered in large rocks. Those rocks would prevent any fine-grained material from being stirred up and captured in the tag SAM head. Another similar scenario is if the tag SAM were to touch on the edge of a boulder and become tipped up. In that case, when the gas bottle fires, much of that gas escapes out the side, not churning up the material that we want to capture. The day of tag is going to be really exciting, but the excitement for our team doesn't end there.
We have to verify that we have a proper sample.
First, we're going to image the tag SAM head by sticking it in front of one of the cameras. Then we're going to do a maneuver called the sample mass measurement, in which we stick out the arm and we spin the spacecraft in order for us to decide if we've collected enough mass to be able to stow the sample and return home, or if we have to try again.
This is the culmination of a lot of work. It's probably one of the most exciting missions that I've worked on.
It is really exciting to know that we're finally going to be able to touch the surface of the asteroid and collect the sample to return back to Earth.
After its discovery in 1999, our first hints of what Asteroid Bennu looked like came from the Arecibo Observatory. Then, as the OSIRIS-REx spacecraft made its way to Bennu, the asteroid grew in detail from a few tiny pixels to a surprisingly rugged world, littered with giant boulders. OSIRIS-REx arrived